In my last video, I talked about how soluble something is in water depends on two competing energetic factors, which is the lattice enthalpy, so breaking the bonds within your salt, and then the hydration enthalpy, which is taking those gaseous ions and adding water to them to form that solvated ion. So the hydration enthalpy, so how much enthalpy heat you're getting out when you're forming those bonds between water and your metal ion, or your, I guess, anion in this case, could be, it's governed by, let's see, if you have a high charge and small radius, your enthalpy of hydration goes up. And then the typical value you're looking at here is the charge of your ion over r squared, the radius of your ion. So again, this is the charge of lithium is +1 is Z. Okay. And the reason for this is because we have our, let's say, our coordination shells, or I guess hydration shells. And also coordination numbers. So when I say coordination number, I mean how many things are bound to the metal center. So for example, if we have a copper 2+ ion, here's copper. Copper 2+ in water is blue, but it has 6 waters bound to it in an octahedral geometry. And then overall, this species is 2+. So this is the solvated copper ion. So this is kind of what you expect when you say copper 2+ aqueous. And then so this coordination number equals 6. If we think about other ions, so let's say we have a different metal ion. Oops, let me draw this picture. Here's my metal, and then I have some sort of charge on it. So it has that first, so the coordination number. So let's say I'm just going to draw 4 in this case. OH, and again is bound through the oxygens because we have our delta minus associating with the positive charge of the metal center. Oh, and then one thing I want to point out is that this is from the lone pair of the oxygen going to the metal center, so it's a dative interaction. So if my metal center is very highly charged and a small radius, it's going to be pulling that electron density from the oxygen very close to itself, and that will induce a large positive partial charge on the hydrogens. And so this partial charge that's induced is dependent on how the Z over R squared of your cation. And then so this might end up, if we're polarized enough, we'll attract a second shell of water molecules, which will also interact. OK, I won't draw all of them. But suffice it to say, what the result is that here is our first coordination shell. So here's our first shell. So these are the water molecules directly bound to the metal center. And then out here, we have our second shell. And these are the waters that are still attracted to this positive charge, but it's bound to just the first shell of waters. So if your ion is polarizing enough, if we have a high enough Z or a small enough R, so this is very big, then we can carry the metal ion, in addition to carry around the waters that are directly bound to it, we can carry around the outside second shell or maybe third shell even. And so it's traveling around solution as this big fat ball of water. And they're all kind of stuck together. Of course, dynamic, but we have this large hydration number. So basically, if we have, oops, excuse me. So we have high Z over R squared. We have a high hydration number. So as a result, for example, lithium can carry around more than 6. I think I'll show the number in class on Wednesday, or Monday rather. But it's a very high hydration number because it has that charge, but also the radius of lithium is very, very small. OK, so the reason this is important is because enthalpy, right, how exothermic your reaction is how many bonds you form. So the higher your hydration number is, the more heat you release upon hydrating your ion. So your hydration enthalpy is proportional to Z/R². And so as a result, if we're comparing the solubility of lithium chloride versus potassium chloride, even though potassium chloride is more polar, and you might think it should be more soluble in a polar solvent like water, lithium chloride has that high hydration number of lithium compared to potassium. So what we're saying is enthalpy of hydration of lithium is greater. I guess I meant greater in magnitude. It's more negative than the enthalpy of hydration of potassium. And so lithium chloride is actually more soluble than potassium chloride in water. And then a second follow-up for why hydration enthalpy and hydration numbers matter is if you want to think about the states of salts, if we try to isolate a salt, let's say magnesium, magnesium has +2 charge in a small radius, so it has a high Z/R². And then so it's very, very difficult to get it anhydrous, to get all the waters off. So it travels around as a hydrate. Similarly, lithium perchlorate is a trihydrate, right? So the lithium likes to hold onto the waters very, very well. And then versus rubidium perchlorate, which is way further down. Rubidium is huge. So because the R is very big, this Z/R² component is very small. And then so it doesn't have a high enthalpy of hydration, so this can be anhydrous easily. If you leave it outside, it won't absorb water. So hydration numbers and enthalpy, they matter. And then so just in terms of predicting solubility, it's really difficult because we have these two competing factors, the enthalpy of hydration as well as the lattice enthalpy, and they both are related to similar things. So I won't ask you to predict a priori whether something should be very, very soluble or not, but you should be able to rationalize trends if I give you data and explain reasons why those data are like the way they are.